So now whenever we define a circuit, okay, it is with respect to a basis, that is, it is with respect to a set of functions which we allow to be the gates for that circuit. So now what are some of the standard bases that we use? Okay, so firstly we have so examples of some standard basis. So basis is the plural for basis. So what are examples of some of the standard bases? So we have the De Morgan's basis, which is represented also as omega. It consists of the gate and, or, and not. Okay, we have the basis B2, which is essentially all Boolean functions on two variables. And how many Boolean functions do we have on two variables? So there are a total of 16 different functions. So the size of B2 is 16. So any gate can be any one of those 16 different functions. Another a very commonly used basis is the basis which has doesn't have a name. So we have the NOT gate, and then we have unbounded OR and unbounded AND. Okay. So basically we have OR gates that can take arbitrary number of inputs and AND gate that can take arbitrary number of inputs. The way they are defined is exactly the same. That is, an OR gate with an arbitrary number of inputs is 1 if at least one of its inputs, if at least one of its input is 1, and an AND gate with an arbitrary number of inputs is 1 if all of its inputs are 1. Okay. So these are some of the bases, but there are other interesting bases also that that one can study. Okay, so here is a couple of very simple results. So the first one is of course a fact. So there are a total of 2 to the power n functions over n inputs. Okay, so suppose if I consider a Boolean function going from 0 1 to the power n to 0 1, how many such functions are possible? Okay, how many different functions can I have that take an input string and produces a single bit as an answer? Okay, so first of all, note that the total number of inputs that are possible is 2 to the power n. Okay, if I have n input variables, each variable can take 2 different values as inputs. So there are a total of 2 to the power input, 2 to the power n inputs. Now each input can have 2 outputs. Okay, so for each input, either that input can be mapped to a 0 or that input can be mapped to a 1. Okay, so therefore there are a total of 2 to the power n different functions over n variables as input. Okay. Now when we have a circuit over n variables, okay, so now we can actually compare. Okay, so we can compare that. Okay, on one side I have this many functions, and on the other side how many circuits do I have that that can actually compute those functions. Okay, and then we can actually compare that. I mean, it allows us to give bounds on the size of circuit. Okay, so my size, I mean, my circuit should have size at least so much, so that it is able to compute each and every one of those 2 to the power n functions. Okay. So next is we define the star size of a circuit as the number of gates not including the NOT gate. Okay. So if I count only the number of non-NOT gates in a circuit, that is what is called the star size of that circuit. Okay, so and often it is interesting to look at the star size, because one can often use standard techniques and bring down all the NOT gates to the input level. So what one is left with is only the non-NOT gates. Okay, so the star size is often a interesting parameter to look at. Okay, so here is the first result that we will see. Every Boolean formula has a circuit of star size at most n into 2 to the power n. Okay. So any Boolean formula. So we have a sorry, every Boolean, not formula, every Boolean function. So we take any of those 2 to the power n many Boolean functions over n bit input. So every Boolean function has a circuit of star size at most n into 2 to the power n. Okay. So again, to be more specific, every Boolean function on n variables has a circuit of star size this much. So how do we prove this? So the proof is actually quite simple. So we take the Boolean function and we look at the truth table of the Boolean function. So consider the truth table of the Boolean function. How many rows will there be in the truth table? So it will have 2 to the power n rows, and in each row, basically the number of columns that you would have is n columns. Okay, corresponding to each variable. So each row corresponds to each setting of the variable, and each column corresponds to a different variable. Now the value of the function can be thought of as taking an OR of all the rows, and inside a row, it is basically taking an AND of all the what are known as literals. Okay, so whatever, so if a variable is set to 1 in a particular row, you take that variable in its positive form, and if a variable is set to 0 in a particular row of the truth table, you take the negation of the negation of that variable, so not of that variable. Okay, so therefore every row has, so okay, we consider what is known as a sum of product representation. So let me write this, sum of product representation of this function. Now in this representation, every row of the function is represented by n minus 1 AND gates. Okay, and so there are 2 to the power n times n minus 1 many AND gates, and then the way we combine all these products or all these AND are using OR gates. So we have a total of there are 2 to the power n OR gates. In fact, to be more specific, there are actually 2 to the power n minus 1 many OR gates, but that's okay. 2 to the power OR gates. So therefore, the total number of gates is equal to 2 to the power n into n minus 1 plus 2 to the power n, which is equal to n times 2 to the power n. Okay, and we are of course not counting the NOT gate, so this is the star size. Okay, so any Boolean function on n variables can be represented by a circuit having star size at most n into 2 to the power n. Okay. So this gives us an upper bound. Okay, so basically an upper bound on the circuit size. But note that this upper bound is actually quite non-trivial, I mean quite trivial to obtain. Okay, and this is a very large upper bound. Okay. Now what if I ask questions such as this, that if I, let's say, bound the size to be polynomial, what kind of Boolean functions are computable by circuits that have polynomial size, or what kind of functions cannot be computed by circuits that have polynomial size. Okay, so these questions become much more interesting. So as we go along this course, we will look at more and more such type of questions, and we'll also look at various types of circuits. So not just any arbitrary circuit, but circuits that have depths, circuit whose depth is bounded by something, circuit which allows a certain type of gates, and so on. Okay, so I'll stop here today. Thank you.